Okay. So we'll start with a reminder or recalling what the definition of the derivative of a function of a single variable was. Okay? This is what we spent a lot of time with last year in Maths Fundamentals. So that's in this first section here. So recall we dealt with functions from the real numbers to the real numbers, so-called real valued functions. And we had the concept of the derivative of one of these functions, okay, which told you the rate of change of the function. How fast or at what rate the values of the function were changing, whether they were increasing or decreasing, with respect to changes in the variable of the function. Okay. So the definition, we define this formally as a limit of a ratio of changes. Okay. So this symbol here, f dash a, is the derivative of the function f evaluated at the point a. So a is some point in the domain of the function, and the derivative was the limit of this quantity. So on the top we have the absolute change in value of the function. F of x is some other point, some point close to a, some point that's going to be converging to a. So we're looking at the difference in values between f of x and f of a, f of x minus a, but we're looking at the relative change, relative to the change in the value of the variable of the function, the argument of the function. So that f of x minus f of a is divided by x minus a. Okay, and we take the limit of that quantity as the parameter x approaches the fixed value a. And that gives us our quantity if that limit exists, and if it's the same limit as you approach the point a from either side, then we say the function is differentiable, and the value of that limit is the derivative of the function. Okay, we also have it here, the second equation. I mean, there's various types of notation, so we can also use that df dx notation for the derivative. And sometimes this limit definition is slightly reformulated. Instead of you thinking of x as a separate point from a and the point x getting closer to a, instead we think of a little difference, h. So h is like an offset from the fixed point a. So instead of looking at f of x, you look at f of a plus h minus f of a, and h is just representing the change in variable, change in value of the argument of the function. Okay, but these two definitions are of course equivalent. Okay. And just things to look at to remind yourself and revise in this initial week, all the properties of calculus of functions of a single variable that you looked at, okay? So the fact that differentiation was linear. When you differentiate a linear combination of functions, the derivative of that is just the corresponding linear combination of the individual derivatives. Things like the product rule, how to obtain derivatives of products of functions. Things like the chain rule, how to obtain derivatives of compositions of a collection of functions, and so on. And then there's a whole host of standard results, standard derivatives of standard functions, polynomial functions, trigonometric functions, exponential function, the logarithm, and so on. Okay, so those are things if you're a bit hazy on them or they're a little bit towards the back of your mind, do sit down and revise those topics. Look over your first year notes or use some of the books I've mentioned already there to bring all that material back to mind as well. Okay. So let's start looking at functions of more than one variable. Okay, so the next the easiest examples of those to look at, of course, would be functions of two variables. Okay, so these are functions which have two separate independent inputs. So we're no longer thinking of a f of x. Now, typically, we're thinking of a f of x and y. So x and y are two independent arguments of the function. And you can have, but we can have functions of any number of variables, of course, and we'll talk about the derivatives of those. But to have a first look at it, we'll just focus on functions of two variables. Okay. So we have these things called partial derivatives of functions of two variables. Okay. So let's look at the first one. The first one, see, because we have two variables, there's no longer a single derivative. But if there's two variables around, then we can differentiate with respect to either of the variables. So we've got two partial derivatives for a function of two variables. Okay. So for this function f, and we're going to use x and y as the arguments, so we've got the partial derivative of f with respect to x. That's shown in equation 1.3 there. Now here initially I'm using the similar notation to the df dx. But when it's partial derivatives we're talking about, we generally don't use the Roman version of the letter d. D we're familiar with from English, but we rather use this alternative d, which I think which is more like something from the Greek alphabet. It's not exactly the Greek letter delta. We've got the Greek letter delta here on the right-hand side of 1.3. But we maybe use this symbol to look something like it over there. You still kind of read it as df dx or partial df dx. Is kind of how you read it out loud. And this is the derivative of the function with respect to x. Now, again, it has a definition using limits, and it looks very similar to the one variable case. But because there's two variables there, there's something slightly different going on. So again, we look at a limit of the function. So this version of the definition is like the 1.2. Okay, so we're dealing with an offset, and we're letting in 1.2 was h, letting that offset approach 0. Okay, here the offset is called delta x. Okay, so you're familiar with using the quantity delta x. Think of that as a single quantity, not a product of delta times x, but just a single name. Delta x represents a change in the value of the variable x. And we're letting that change, delta x, approach 0. We're taking the limit as delta x approaches 0. Okay, the limit of what? Well, again, it's similar to before. We're taking the absolute value and change of the function relative to the change in value of the argument. Okay? But we're only looking at making changes to the x variable here. Okay? So we're looking at f evaluated at x plus delta x and y, and comparing that with the value of f at x and y. Okay? So it's the same y in both function values there. Okay? So the x variable is different here. First, it's x plus delta x. Excuse me, it's x plus a little bit. And the second one is just x, but it's the same y in both expressions there at the top. And again, that's divided by delta x, which is the change in value in the argument. So if that limit exists, we say the function is differentiable with respect to x, and the value of it is the value of the derivative evaluated at whatever these base points x and y are. And of course, you can do a very similar thing with taking a partial derivative with respect to the y variable. Okay? Definition looks the same, except this time stuff is going on with the y variable. So we're taking a limit as the change delta y goes to 0. So delta y is a small change in the y variable. Again, the difference in values of the function, f of x and y plus delta y, minus the value of the function f evaluated at just x and y. Okay? But there, in this second version, x is remaining the same value throughout. Okay? The value in the second argument here on the top is changing, so it's y plus delta y, and delta y is converging to 0. But the first argument, x, always remains at the same value. And again, if that limit exists, we say the function is differentiable with respect to y, and it has that value when evaluated at the base point x, y. Okay, so those are our limit definitions of the partial derivative. So let's straight away jump in and have a look at an example here. This is example 1.1. I'll switch to the overhead. Okay, so we're looking at a fairly approachable function here, just a single polynomial term, but of course it's a polynomial term in two variables. This thing seems a bit sticky. I'm just going to go. So it's x squared times y. That's the formula for our function, and let's look and see if we can obtain the partial derivatives, the two partial derivatives of this function. I think all the steps are there in the book. Well, they're there for the. Let's go through it. So df dx, we'd be looking at the limit. Well, let's switch to this h. It's a bit easier for writing it out here. Okay, so that's the quantity we're looking at. Okay, I'll switch away from the delta x. I'm just going to write h. It's a bit simpler for writing it on the page. Because that's another thing, another skill and confidence you need to continue to develop is don't be getting too attached to particular notations. You're going to have to continue to, or deepen your appreciation of formulae and things like that. Don't get too attached to the fact that I'm using an f or an x and a y. You have to be able to recognize these things when they crop up using other names as well. So because we've got the formula for f, we can actually replace those f of x, y, and so on with their actual values in terms of x and y and h. Okay, so just using the rule at the top of the page, f of x plus h and y is, of course, x plus h all of it squared times y, and f of x, y is x squared times y. So, what can we do here? Well, we could expand out the bracket. This gives us x squared plus 2xh plus h squared, and that's all of it multiplied by y, and then we're subtracting x squared times y, and that's all still divided by h. But that can simplify down, of course. X squared times y minus x squared times y, so that's going to go. And the h will divide into what's left. So we're left with that term after we cancel out the x squared y's, because that's positive and negative there, and then divide through by h, and what's remaining. So we've got 2xy plus h times y. We're taking the limit of that as h approaches 0. The values x and y are fixed here, because this is a limit as h approaches 0, so x and y are just fixed at some particular values. So the fact that this is h times y, this is going to get rid of that term, and you're just going to be left with 2xy. If there's no h involved in 2 times x times y, so it's just a constant value as far as this limiting process is concerned. But the h times y, well, y is some fixed value multiplied by h, but h is converging to 0, so the h times y converges to 0. So this is our result, if you like. The partial derivative of this function f with respect to x is 2 times x times y. Okay? Let's go to the y derivative as well. Is that okay? Any questions? Any confusion you need to clear up there? Yeah? Sorry? Why did you get rid of the hy? Why did I get rid of the hy? Well, because it's inside a limiting process, yeah? h times y. But the h is getting smaller and smaller and converging to 0. So h times y is just going to be 0. Any other queries? Okay, let's jump in, try and do the y one. Everybody got that, yeah? So df dy, according to the definition, it's this. It's that now we're varying the y variable, the second variable. But again, we know what the definition of this function f is. It's the first variable squared times the second. So this is going to be x squared times y plus h minus x squared y all over h. Simplification is a bit easier here. It's more direct. We know all you have to do is cancel the x squared y and divide by h. And you're just looking at this limit here. So h is cancelled, don't they? You've got x squared times h in the top, h in the bottom. It's got the limit as h approaches 0 of x squared. But as far as this limiting process is concerned, x squared just remains fixed at whatever value it has, because there's no h involved there. Okay? H is an independent little variation in the value of the y variable. So this just remains at x squared. Okay. Now that procedure is working out or obtaining partial derivatives using the limit definition. Or sometimes it's called by working from first principles, working straight from the definition. But of course, what you may have noticed there, or what we use in practice instead, is something more like just using the standard rules of differentiation that we already know from one variable calculus, together with an important principle. Okay, so I'm going to switch back to the laptop. The important principle, and you can tell it's important because it's in boldface. So rather than, instead of using the limit definition, we'll instead use this principle here, which is this quote in the middle of the page. So if we're differentiating a multivariable function, f, with respect to one of its variables, let's say x, what we do is we treat the other variables as if they were constants. So in our two-variable case here, we've got f of x and y. So if we're differentiating it with respect to x, we pretend for a moment that the y variable, although we know it's a variable and it can take many values, but we pretend for a moment that it's fixed. So then what we're looking at then is no longer a function of two variables, it's now a function of one variable. It depends on x and there's some value y stuck in there in the formula. So you can now just use the same results, rules, and principles from single variable calculus for finding that derivative, that partial derivative with respect to x. Okay. So if you look back at what we just did, so this f, which is x squared times y, if we follow that principle, so we look at that formula x squared times y, we want the partial derivative with respect to x. So we consider the other variable y as just some fixed constant. So what we're looking at now is some fixed constant y times x squared. That's just a function of a single variable x. We know what its derivative is. We know how to differentiate polynomial terms in a single variable. The derivative of x squared is 2x. And it has this other factor y multiplying it, so that's also going to be there in the derivative as well, by linearity. So by using that principle, we can look at that and say that the derivative with respect to x of that function is 2xy. Okay, derivative of x squared is 2x, and the y, by linearity, that constant y, whatever it is, stays there as a factor. Similarly, to take its derivative with respect to y, taking its derivative with respect to y, we now treat the other variable x as if it were a constant. Treat x as some fixed constant. So what you're looking at is just a constant times y. What's the derivative of a constant times y? The derivative of a constant times y is just whatever the constant is. The derivative in the normal one variable sense. So that constant is x squared in this case. So df dy, partial df dy then is y squared. So those were the answers we found using the original limit definition. But in practice now we can use this principle for doing this instead. Okay. So that's why I said at the start, you need to have all the standard calculus stuff you learned in mathematics fundamentals. You need to bring all that to the top of your mind again. So you're going to be using that all the time. Not only in this unit, of course, but in your other studies as well. Okay. So we'll be very much building on all of that. Okay, it's a bit more of a detailed example there in 1.2. So you can try working through that. But I'll just finish today. There's a little section, if you skip a couple of bits on there, there's this section on the graphical interpretation. So I just want to finish this just in the last couple of minutes. I think we'll look at it again next time as well. So what do these partial derivatives mean? Well, you can obtain a graphical interpretation of them by interpreting them as tangents or slopes of the tangent lines to certain one-variable curves. Okay. Well, we don't have that much time to look through this, but we'll have a quick look at it, and we'll come back to it again next time as well. Okay, so what's this here? This blue, what we're looking at there is a blue surface. Okay, so it's a three-dimensional surface. The vertical coordinate, the height of it is the variable z, and the height is defined using a two-variable function, f of xy. The function we're actually using here is have I got it written up there? Yeah, it's sine of x times y. At the top there, the definition is f of xy is sine of x times y. And on this curve, we've got cross-sectional, on the surface, sorry, we've got cross-sectional curves, and those are the red and green lines. And those are, I'm just going to change, A and B, the base point at the moment is set to the origin. I'll just change one of them to a different value. And change the other one a little bit as well. So then I've moved the base point off the origin there. So the base point is at the intersection of the two curves. And we have this notion of the cross-section of the surface parallel to one of the coordinate axes. So the red curve is running into the screen there, and the green curve is going left to right. So the green one is parallel to the y-axis. See, y is changing across the bottom there. And the red curve is parallel to the x-axis. Now down below, I've straightened these curves out, taken them out of the 3D view, and just given them their usual two dimensions. These are just cross-sectional curves to the surface, so we can draw them in 2 dimensions. So you see the axes there with the red curve, I've got the x-axis on the horizontal and the height z on the vertical. So I've removed the y-axis, okay, because y is just fixed. See, for that red cross-sectional curve, y is always fixed at some particular value. Well, whatever this value y on the y-axis is, every point on that red cross-section has the same y variable. So we don't need to bother drawing it, because y is constant there. And similarly, there's the green cross-sectional curve. Now, the base point there I've reproduced on these two curves again. So what is the base point out of interest? The base point is 1.96 minus 0.63 approximately. Now the partial derivative with respect to x for this function, when you evaluate it at this base point, it comes out negative 0.2. You can see here on the cross-sectional curve at the base point, the cross-sectional curve is actually decreasing at the base point. So decreasing curves have tangent lines that are sloped negative. So the negative value and the fairly low value of that partial derivative with respect to x corresponds to the low decreasing rate of change of the cross-section parallel to the x-axis. Some fixed particular value of y. When you look at the green one, so the green one is the curve which runs parallel to the y-axis. So that's at some fixed value of x, but its y is changing along the green cross-section. The base point we're talking about is that point down there in the valley. It's in the intersection between the two. This point down here. But when you look at the cross-section curve, here's the base point reproduced on it. The cross-section with respect to y, that's increasing at this point. Okay? So it's gone through its minimum value, and again, it's sharply increasing. So the y derivative there, that notation f with the subscript of y, it's explained in the notes, that's the partial derivative with respect to y of this function. And when it's evaluated at that base point, we get a positive value, 0.6. That corresponds with the positive slope of the tangent line to the cross-sectional curve at that point. Okay, so it's a short lecture, this first one, because we had all the housekeeping stuff at the start. I'll see you, it might be me taking the lecture later this week. I'll talk to Steve. So I'll see you later on.